Let's look at implementing Boolean functions with a multiplexer. Recall we did implement Boolean functions with a decoder. A decoder would decode the inputs to a minterm. So once we are in this case, we have a 3x8 decoder. Our three inputs could be decoded to 8 minterms that could represent a truth table. So each of those minterms then we could put an external OR gate and implement the function as a sum of minterms. And this is an example of the full adder where we have two outputs, the sum and the carry. So the decoder's outputs select the minterm represented at by the inputs. The external OR gates produce the sum of minterms for our outputs. Well, a multiplexer is essentially a decoder with an OR gate external. So it only has one OR gate external, so it can only implement one function as opposed to this one implementing two functions. So here's our multiplexer, which has the decoder, but it also has the one OR gate internal if we have here showing a 4-to-1 multiplexer. If we had a double 4-to-1 multiplexer, then we could produce two outputs. We showed a quadruple 2-to-1 multiplexer. Here we show what we used for our block diagram for a multiplexer. We said typically a multiplexer uses this cutoff rectangle. It's a special symbol so we can recognize it in a logic diagram. So here again we have our 4-to-1 multiplexer with the two selects. What we'll be using for our block diagram is just a square block like an IC, and we'll put the selects at the top and the four inputs down here at the bottom. And this, what we looked at earlier, is we showed the selects coming up into the AND gates and they came down at the bottom. So we have to determine what our inputs are defined by in terms of the block. So let's look at an example and we'll use this type of a block. So if we wanted to decode a 3-input function, this is showing how can we do that with a 4-by-1 multiplexer. So with a 4-by-1 multiplexer, then what we have to determine is what do we put at the inputs of the multiplexer and what do we put at the selects of the multiplexer. So if, for example, if we selected a 0, 0, if our selects here, we'll put this here, where's a 0 and a 0, then we'd be selecting input 0. If our selects were 0, 1, we'd be selecting input 1, and that would show up at the output. So on our truth table, where do we have a 0, 0? Well, we have a 0, 0 at x, y in the first two rows. We have a 0, 1 at 0, y in the second two rows. And the third two ones we have, so here are our minterms, 0, 1, 2, and 3. So if we use here x for S1, let's just erase what I wrote here for 0, 0. If we use instead, we use x at S1 and y at S0, then when we're at 0, 0, what we want f to be is a 0 when z is equal to 0 and a 1 when z is equal to 1. So in this, when x and y are 0, 0, we just have f is equal to z. So at input 0 here, we just need to wire z. So now we're using our three inputs of the truth table to create this function. When x and y are 0, 1, then what we have is an inversion here, right? So now we have f is equal to z prime. When z is a 0, f is 1. When z is a 1, f is 0. So we're only going to have these different options. Here we just have f is equal to 0, and here we just have f is equal to 1. So if x and y were 1 and 0, we would be selecting 2. Our input would, the input up here would select 2, and 2, we'd want to put out a 0. So we have z at input 0, z prime at input 1, 0 at input 2, and 1 at input 3. So our method is just to take our truth table and break it out into sections. And it's easiest to do it this way, where we let the most significant bits be used as the selects, and we use the least significant bit to determine what goes into the inputs to select our function. So then our function, our inputs to our multiplexer will either be that third bit, in this case it's z, so we can either have z, z prime, 0, or 1. There are no other possibilities to be able to represent the function here with respect to this truth table. So let's take a look at what we would do if we had a larger truth table. Let's say we had a 4-input truth table, or a function of 4 variables represented in a truth table. Then we could similarly use a similar process if we had an 8-to-1 multiplexer. So now what we'd want to use for our inputs, at S2, we'd have our most significant bit, that's A. So S2, we'd have A, at S1, B, and S0, C. So now we can still break up our truth table in the same way. So we have our input 0 is in these first 2 rows. At input 0, what we have is F is equal to D, right? F is equal to D here, and it's equal to D there. So we'll just put at input 0 a D. If we, when A, B, C are equal to a 1, we still have F is equal to D here, right? So F is equal to D. It's the same, so we get D there. If we look at 0, 1, 0, at 0, 1, 0, or what we'd call a 2, a binary 2, well now F is equal to D prime, right? Because when D is 0, F is a 1. When D is 1, F is a 0. So we can draw a D prime. Instead of drawing the inverter, we'll just do a D prime here. And then at 3, this is just 0. F is equal to 0. F is equal to 0. Once again, here, F is equal to D. F is equal to 1. And F is equal to 1. So we get a 1 at 7, a 1 at 6, a D at 5, a 0 at 4, and a 0 at 3. So understanding the process, it's easy enough to design this way. The simplification is really just taking our truth table and breaking it into every 2 lines, right? And we use the first 3 inputs for our selects, being careful that we do it in the correct order. If we swapped A and C, we'd be in a little bit of trouble. And then again, all we're going to possibly have at our inputs are either D, D prime, 0, or 1. So this just shows a logic diagram. So with that process is easy enough if we have, for example, 4 input function and an 8x1 MUX. Well, what if we had the same 4 input function, but we wanted to implement it with just a 4x1 MUX? So now we have to take our truth table, instead of breaking it into every other row, we have to break it into 4 rows, right? So the first 4 rows now is where A and B are 0, 0. So if we still put A at S1 and B at S0, now we're going to have more possibilities for F other than just 0, 1, D or D prime, because we have to decide between C and, C and D, it doesn't have to be an logical and, what our function is. In this case, it looks like it's still just the same as D, right? So 0, 1, 0, 1. So here we still just have F is equal to D here, so we'll just put a D at 0. If we go to 1, then what we have is F's not equal to D, it's not equal to D prime, it's not equal to 0 or 1, but it's the only time it is a 1 is here, and that's when C and D are both 0. So this looks like F is equal to C and D not, or the NAND of CD. So what we can put here is a little NAND gate with C and D. So we will need some external logic, just like we do with the decoder if we just use a 4x1 MUX. If we come down here and we look at minterm 2, or it's not really minterm 2, but when A and B represent a binary 2, In that case, it looks like we only have the 1 right here, and that's when C and D are both equal to a 1. So that looks like F is equal to CD. So then we'll have an AND gate, CD, and that's what we'll go to 2. And down here, it looks like F is just equal to a 1. So we can draw a 1. That's really pulling it to 5 volts, but logically we'll just show a 1 there. All right, so I think that's it for this video.